In the last few lectures, we were discussing the laminar flow in a pipe. This is a unidirectional flow in a cylindrical pipe in which the velocity is only along the axis of the pipe. There is no velocity perpendicular to the axis. Unidirectional, fully developed, that is, the velocity is independent of streamwise location. As you go along the axis of the pipe, there is no change in the velocity. The velocity depends only upon the distance from the axis, the radial coordinate. We had derived this by doing a shell balance over an annular cylindrical shell in which the thickness in the radial direction was delta r and the thickness in the axial direction was delta x. And in this cylindrical coordinate system, there is a force in the x direction. So, the balance was for the x momentum along the axis. Forces on the surface of this cylindrical shell in the x direction are due to the shear stress at r and r plus delta r and due to the pressure at x and x plus delta x. The pressure is varying in the x direction at steady state. We had derived the momentum balance equation, if you recall, and the momentum balance equation was of this form, where tau x r is the shear stress, the force in the x direction acting at a surface whose outward unit normal is in the r direction, and there was a pressure gradient delta p by delta x. For a unidirectional flow, I had demonstrated to you that the velocity is independent of the x direction, the flow velocity is independent of the x direction if the fluid is incompressible, dVx by dx is equal to 0. What that implies is that the pressure gradient is a constant. The second derivative of the pressure with respect to x is 0, which means that the pressure is a linear function of x. Pressure can be a function of time, because the pressure at the inlet and the outlet is in general a function of time, but the pressure variation from the inlet to the outlet at any instant of time is linear for this unidirectional fully developed flow. The pressure could be unsteady because the inlet pressure varies, the outlet pressure varies, but at each instant of time the pressure, the flow is fully developed, that is, the pressure is a linear function of x, velocity is independent of the axial coordinate. So, those were the features of this pressure driven flow. Based upon that, we had derived the velocity for a Newtonian fluid, and derived an expression for the velocity as a function of pressure gradient, the maximum velocity and the shear stress. The shear stress was a linear function of position, the velocity was a parabolic function, a Hagen-Poiseuille flow. And based upon that, we had derived an expression for the friction factor as a function of Reynolds number for a laminar flow for a Newtonian fluid. The friction factor, the fanning friction factor is 16 by the Reynolds number, as you would expect for a laminar flow where inertial effects are not important. The drag force has to be only a function of the viscosity, the velocity and the diameter, and it is a dimensional necessity that the friction factor has to be proportional to 1 over the Reynolds number. We had solved an example for this for a laminar flow, and I had also derived for you the flow of a power law fluid. Here the relationship between the shear stress and the pressure drop at steady state is exactly the same as we had for a laminar flow. However, the relationship between the shear stress and the velocity gradient is different. This is a power law fluid. Nevertheless, we can go through the same procedure and derive an equation for the friction factor as a function of Reynolds number for a power law fluid as well. We had derived it in this case, the relationship between the friction factor and the Reynolds number, where the dimensionless Reynolds number now is expressed in terms of the power law index and the flow consistency index, both of which are defined for a power law fluid like this, and the Reynolds number has to be expressed in terms of the flow consistency index and the power law index instead of the viscosity. If you recall, when we had our discussion of the flow in a pipe, the friction factor correlations, I had said that the flow is of two kinds. One is a laminar flow and the other is a turbulent flow. Okay. The characteristic of these two are very different. Okay. For a laminar flow, the streamlines are straight and smooth, steady, that is at a particular location. If you determine the velocity as a function of time, the velocity is a constant. Here I mean the fluid velocity. We had discussed before the relation between how the fluid velocity is calculated from the molecular velocities. In this case I am talking about the fluid velocity. The fluid velocity, the streamlines are straight, the velocity is steady at a particular location in time. At a particular location, if you measure the fluid velocity as a function of time, it is independent of time for a steady flow, and there is no cross stream fluctuations in the velocity. Therefore, the momentum transport perpendicular to the flow takes place only due to molecular diffusion, and this mechanism of molecular diffusion we had used in order to find out the conservation equation. If you recall, the conservation equation we had was 1 over r d by dr of r tau x r is equal to partial p by partial x. That was the conservation equation that we had determined at steady state, and for this tau x r we had written tau x r is equal to mu partial V x by partial r. Thus, momentum transport is due to molecular diffusion due to the viscosity. At a Reynolds number of approximately 2100, there is a transition to a turbulent flow. The characteristics of the turbulent flow are very different from those of a laminar flow. The velocity is more plug like at the center and has sharper gradients at the wall. So, this is the x direction, this is the r direction. The velocity is more plug like at the center and has sharper gradients at the wall. In this case, at any instant of time, if you look at the velocity at a particular location, there will be fluctuations in the velocity in all three directions as a function of time. If you look at the velocity, the streamwise velocity V x, it has an average value of course, but it will be fluctuating about that average. It will be fluctuating about that average value. The velocity in the streamwise direction V x. There will be fluctuations in the cross stream direction as well. If I put a Cartesian coordinate system at this particular location, and consider the velocity in the three directions at that particular location, V y, on average it will be 0 because there is no average velocity perpendicular to the axis. However, there will be fluctuations in V y as well. There will be fluctuations in V y as well, and there will be fluctuations in V z as well. So, the velocity fluctuates in all three directions. The magnitude of the fluctuations in a turbulent flow is comparable to the mean velocity. These fluctuations transport momentum. So, the primary transport of momentum perpendicular to the flow in a turbulent flow is primarily due to the fluid velocity fluctuations, okay, not due to molecular diffusion. And because of that, we cannot use this constitutive relation, okay, to describe a turbulent flow, okay, because there are fluid velocity fluctuations that are driving the flow. Recall that I had said that in a laminar flow, if you write the momentum conservation equation perpendicular to the flow, you will get identically 0, because the fluid velocity perpendicular to the axis is 0. Not so in a turbulent flow. There are fluid velocity fluctuations, and therefore, you will not get 0 if you write the momentum conservation equations in the 3 directions. Therefore, to solve for a turbulent flow, you would have to write down the momentum conservation equation in all 3 directions, okay, and then solve for that. Okay. The exact nature of turbulence in these kinds of flow is not yet understood. However, what we do know is that the friction factor in a turbulent flow is much higher than that in a laminar flow. Recall that the friction factor in the laminar flow was given by 16 by Re. Okay. In a turbulent flow, we only have approximate expressions for the friction factor. I had discussed for you the Colebrook correlation for the friction factor in a turbulent flow. It is an approximate, but useful correlation for making estimations. Okay. It is of the form 1 by root f is equal to minus 1.737. Okay. The natural logarithm of 1.25 by Re root f plus epsilon by 3.7 d, okay, where d is the pipe diameter, okay, and this parameter epsilon, okay, is an estimate of the wall roughness, okay, is an estimate of the wall roughness. That is, if I look at the wall close to the pipe, the region near the wall of the pipe, and I expand it out, real walls will have some kind of a roughness, okay, and this roughness will cause some secondary flows very close to the wall, okay, in addition to the turbulent fluctuations that are also present in the pipe, and this can affect the friction factor. Okay. Okay. So, these velocity fluctuations close to the wall, due to the fact that the wall is not exactly smooth, can also affect the friction factor. If the wall is perfectly smooth, epsilon is just set equal to 0 in this case. Okay. And you also have other ways of calculating the friction factor. There is the Moody diagram, okay, which basically plots log f versus the natural logarithm of Re, okay, on a log-log graph. Okay. You have a straight line, okay. This corresponds to f is equal to 16 by Re, and at some point you have a transition to a different friction factor curve. Okay. Okay, you have a transition to a different friction factor curve, which depends upon the value of epsilon. Okay. And this decays much slower in comparison to the 16 by Re that we had. This transition takes place at a Reynolds number of approximately 2100. Okay. And I should emphasize that this is approximately 2100, and I will come back and explain why that is so. Okay. So, what is the reason for this transition to turbulence? Okay. What is the reason for a transition from a laminar to a turbulent flow? Okay. It turns out that the laminar flow equations, Okay, the laminar flow equations that I have derived for you here, okay, the laminar flow equations, the solution of that is a parabolic velocity profile. Okay. So, the parabolic velocity profile is a solution of the conservation equations at all Reynolds numbers. That is, for Reynolds number, whether it is below 2100 or above 2100, the parabolic profile of the steady fully developed equations is a solution of the equations of motion. Okay. It is a solution of the equations at all Reynolds numbers. Okay. However, this solution becomes unstable when the Reynolds number exceeds a critical value. Okay. To illustrate this, let me take the example of an object in, let us say, a well. Okay. You could consider this as an object in a well in, for example, a gravitational field, okay, or those who are used to thermodynamics could consider this as an object in a free energy minimum, for example. Okay. This is a stable equilibrium. Okay. The reason is because if I disturb it either to the right or the left by a little bit, the forces that are exerted on the object tend to bring it back to this minimum state. Okay. The forces that are exerted on this object tend to bring it back to the minimum state. Okay. On the other hand, if I had an object on top of a hill like this, okay, located at the maximum point of this hill, okay, and I have a gravitational force downwards, okay, this object is at equilibrium. The forces are all balanced, the upward force and the downward force, the weight of the object and the upward force exerted by this by the hill, these are both exactly balanced, and so the system is at equilibrium. However, that equilibrium is unstable. What that means is that if I disturb this object by a little bit on either side, this object goes to some other state. Okay. So, this is an unstable equilibrium. Okay. So, this is what is called stable, this is what is called unstable. Okay. So, let me write. And between these you have something called a neutral state, okay, where if you displace the object a little bit to the left or the right, it neither comes back or nor goes away. Okay. So, this is what is called a neutral state. If you displace the object either to the left or the right, it neither comes back to its original location nor it goes away from that original location. Okay. So, this was for an object in only one dimension. Okay. A pipe flow is of course much more complicated. Okay. A pipe flow is of course much more complicated. Okay. You have the velocity defined at each location, and each velocity could have three different directions. Okay. Nevertheless, the picture is the same. Okay. If you displace the velocity by a little bit, as you know, in nature there are always disturbances. Okay. If you have a real pipe, there is always some disturbance in the other that is exerted on the pipe due to vibrations in the surroundings, due to atmospheric conditions and so on. that small disturbance will spontaneously take the system from the stable to the unstable state. Okay. This is the classical picture of hydrodynamic instability. Okay. This is the classical picture of hydrodynamic instability, and it holds for various kinds of configurations. Okay. So, for example, in a channel flow, for example, between two plates, okay, where I have a parabolic velocity profile. If the velocity exceeds a critical value, there is an instability of the base state, okay, and this leads to a transition to turbulence. Okay. A pipe flow is slightly more complicated. Okay. It is not the same as a laminar flow. Okay. A pipe flow is slightly more complicated. Rather than having this relatively simple picture, okay, the progression of states from a laminar to a turbulent flow can be more accurately explained as something like this. Okay. Okay. This is the stable state, and then it goes to a state where it looks something like this. Okay. Note that in this case, okay, in this unstable state that I had, any infinitesimal displacement to the right or the left will cause a spontaneous transition. Okay. The system will go to some other state for any infinitesimal displacement, either right or left. In this case, it will not transition for an infinitesimal displacement, but rather because of the displacement beyond a certain amplitude, okay, a finite amplitude displacement. Okay. So, this progression happens as you increase the Reynolds number, okay, as you increase the Reynolds number. Okay. And a further increase takes you to a state something like this. Okay. Here you require a much smaller displacement, okay, for the system to transition. Smaller, but still a finite displacement. Okay. That system, the laminar flow is still stable. Okay. The laminar flow is still stable. It is not unstable to infinitesimal disturbances because it is still sitting at a minimum. However, when the displacement exceeds a finite value, the system undergoes a transition to a turbulent flow. Okay. In fact, the laminar flow is not unstable independent of what the Reynolds number is. Okay. You do require a finite amplitude displacement in order to make the system unstable. Okay. And this experimental confirmation for this, if you take, okay, so I said that transition to turbulence, okay, laminar to turbulent. Happens at a Reynolds number, I was careful to say approximately 2100. Okay. However, we can delay the transition by taking care to damp out disturbances, to reduce disturbances in the environment. And when you reduce disturbances in the environment, the transition, the flow can be maintained in the laminar state at Reynolds numbers of up to 10 power 5. Okay. By removing or by reducing, okay, let me call that as reducing disturbances. Okay, so you can maintain it in the laminar state at relatively high Reynolds numbers by reducing disturbances. Okay. However, since disturbances always exist in nature, typically you will see this transition at a Reynolds number of about 5100. Okay. I should note that this description that I have given you here is simplistic. Okay. It is valid only in one dimension. Okay. For a channel flow, okay, for the flow in a channel, okay, as well as other kinds of instabilities. Okay. So, for example, a heated fluid. For example, if you heat a fluid between two plates, okay. Okay. So, if the temperature variation between the two surfaces is relatively small, right, the flow will the fluid will remain stationary. However, if it exceeds a certain value, okay, the delta T, okay, when it crosses a certain value, you get these spontaneous rolls. Okay. This is called the Rayleigh-Bénard instability, and similarly for rotating fluids you have something called the Taylor-Couette instability. All of these take place by this mechanism that I have given you here, where the system goes unstable to infinitesimal disturbances. In a pipe flow, the system does not go unstable to infinitesimal disturbances, it goes unstable to what are called finite amplitude disturbances. Okay. And the picture is what I have shown you over here. Okay. Recall that the laminar solution is still a solution even at these high Reynolds numbers. Okay. And we had also discussed how the fluid velocity is separated into its mean and the fluctuating parts, and dispersion due to the fluid fluctuating velocities. If you recall, we discussed the Reynolds stress as well as the Reynolds fluxes, okay, when we had talked about dispersion. That dispersion in this case is due to the fluid velocity fluctuations. So, let me tell you some characteristics of turbulent flows. Okay. One is there are relatively large velocity fluctuations in all directions in a turbulent flow. Okay. As I said, at a given location, if you track the velocity, the average of the velocity will be only in one direction, but the velocity fluctuations will be in all three directions. Turbulent flows are necessarily three dimensional. It is not possible to have a turbulent flow in which the velocity fluctuations are only in one or two directions. Okay. The velocity fluctuations necessarily have to be three dimensional. Okay. Highly diffusive. Okay. That is because mass and heat diffusion takes place due to the fluid velocity fluctuations, and the diffusivity or the dispersion coefficient due to the fluid velocity fluctuations are much larger than that due to the molecular velocity fluctuations. Momentum transport also takes place due to the fluid velocity fluctuations, and therefore, these are highly dissipative. Okay. Nevertheless, turbulence is a flow property. Turbulence is a flow property. What I mean by that is that the smallest eddies in a turbulent flow. Okay. So, before that I should say that there is a range of eddies. Okay. Range of length and time scales. Okay. Fluid velocity fluctuations are in the form of eddies, that is parcels of fluid in correlated motion, and these eddies have characteristic length and time scales all the way from the large scale, which is comparable to the flow scale, to a small scale which is much smaller than the flow scales. Okay. So, there is a range of eddies. There is not just a circulation of one particular size, there are circulations of a range of sizes simultaneously coexisting in a turbulent flow. However, this is a flow property. Okay. What I mean by that is that even the smallest eddies, the size of those is much larger than the molecular sizes. Okay. Even the size of the smallest eddies is much larger than the molecular size. Okay. So, in that sense it is a flow property. The large scales in a turbulent flow will be independent of the viscosity of the fluid, independent of the molecular size, molecular length scale. Okay. So, this is, and it can be described by continuum equations. Okay. Since the smallest scales are still much larger than the molecular scales, these can be described by continuum equations themselves. And finally, I should say that this is a feature of high Reynolds number. Okay. You do not have turbulence at low Reynolds numbers. You typically have turbulence only when the Reynolds number exceeds a threshold value. Okay. So, these are the features of a turbulent flow. Okay. I will discuss a little bit more about these sizes of the eddies and the small scales in a turbulent flow in the next lecture. I will continue this discussion of turbulent flow in a pipe. I will see you then.